All right, so today we're looking at titration curves. You guys did a titration already this year that looked something a little like this. Who remembers what was on the y-axis? We used a pH meter and a burette. What was on the y? pH, and then here was the mils of base that we added. We had acid in our beaker, it was HCl, and we had NaOH in here, and you titrated and created this curve. We looked for something called the equivalence point. The equivalence point is the part where the OH minus moles, the moles of base, is equal to the moles of acid. How did you know where to look for it? Where on the curve did you try to find it? The steepest slope, which is kind of in the middle of this sharp rise. So you either took the derivative of that, or you went ahead and just found the average between this point and this point. So this particular curve that we did was what I call a strong curve, meaning we titrated a strong base into a strong acid. I need you to know, though, we could have had acid in the burette and base in the beaker, and our curve would have just looked like this. So not all titration curves go low to high. They can go high to low as well. But what we're going to do now is actually look at the calculations required to create the shape of this curve. First for strong, and then we're going to look at a weak strong titration, where we have a weak acid and a strong base, or a strong base and a weak acid. Compare the curves. So you should be able, at the end of this, just look at a curve and tell me what things were titrated. So we're going to go ahead and start. This is a series of invader problems over and over and over and over again in order to get all our points that we're going to plot. A titration is performed by adding 0.6 molar KOH to 40 mils of 0.8 molar HCl. What's in the burette and what's in the beaker? HCl is in the beaker. KOH is in the burette. So our number of moles of HCl is going to stay the same because that's in the beaker and we're adding to it and adding to it. That is what we're invading. So our equation for this strong situation is invading with OH into the strong acid, making what? Water. So this strong situation makes for very, very simple, easy calculations because it's just stoichiometric table and then immediately finding pH from that. OH minus then, for our first thing here, they're asking, however, before we start this, the pH before we put any base in there. So if we're just taking the pH of that acid, how do I do that? What? Negative log. Negative log of just 0.8. You do that, you should get somewhere around 0.097. We haven't added any base yet. We really are just starting the titration. And so now we're going to start the titration, and we're going to do a stoichiometric table here. So we put moles in our stoichiometric table. H plus is always going to be the same moles. It's not going to change throughout the entire titration. It's 0.04 liters times 0.8, and what do we get? 0.032. That number is going to stay the same. Here we're adding 20 mils of 0.6 molar, so 0.02 times 0.6, 0.012. All right, so who's going to run out in our first invasion? The base, minus 0.012, minus 0.012. I could make water, but we don't care. It's neutral. So we run out of base, and we're left with 0.020 moles of H plus. All right, that's it. How do we find the, can I take the negative log of 0.02? Nope, we got to convert it to concentration. So this is what's different about these. Because we're adding more and more base, we have to take the total from the burette to the original amount. We added 20 mils to the 40 mils already in there, so we're going to divide this by 0.06. So what is that? Say again? 0.333 moles per liter of our H plus, and you take the negative log of that, you should get somewhere. Okay, close enough. Does everyone understand that? It's going to be a fast day of writing, because now we're going to repeat this again. And we're going to calculate the pH after the addition of 40 mils of the base. So OH minus plus CH plus makes water. All right, we're invading the 0.032 mils with this time, I forgot, is it 0.8 molar HCl? 0.8 times 0.6 molar? 8 or 0.8? First off, it can't be 8. 0.6, okay. 0.6 molar times 0.04, so that's 0.024. Because we start the math from the beginning. If I were to start there, I'd have to then only add 20 more mils. We're not adding 20 more mils. We're not adding 40 more mils. We're adding to the 40 mark. So it's a total of 40 from the beginning to where you are on the burette. So we're starting fresh each time. So here, minus 0.024, minus 0.024. So we get 0 here, and this is what? All right, so that's our moles. Our total volume is 80, right? 40 in the beaker, 40 here, so 0.08. So that's 0.1. So the concentration of H plus is equal to 0.1. If you take the negative log of that, you should get a pH of 1. Okay, so we're getting there. We're getting to the point we're going to have equal moles here soon. Not yet. Calculate the pH after the addition of 53 mils of the base. All right, so this plus this. Again, our 0.032 doesn't change. Here we have 0.6 times 0.053. It's 031 something. 0.0318 minus 0.0318 minus 0.0318. So we run out of base. Now we only have 0.0002? No, 04? But how can that minus that be 2? This 2.0? This can't be right. That doesn't make sense mathematically. Oh, okay. So 0.002. There. Moles. Divided by, we have 53 plus 40, 93, so 0.093. So our concentration of H plus then, negative log of that, does this give us something around 2.67-ish? Yep. All right. So one thing I want you to notice is we're already at 53 mils. That's an entire burette full. And look at the pH. Has anything happened? Like we've gone from 0 to a pH of 3. So are we anywhere near 7 yet? Okay, so this is a characteristic of the strong. See how this is pretty flat? It's a very ideal characteristic of a strong titration. All right, now we're going to calculate the volume needed to get to the equivalence point. All right, what is the equivalence point again? Moles of base equals moles of acid. So if we have 0.0032 here, we need 0.0032 there. Well, how do I know how many mils? I know the molarity of this base is 0.6. Molarity is equal to moles over liters. So I can figure out how many mils of that I would need for this to happen. So if I divide 0.0032 times 0.6, I should get 0.0533. Where? 0.0032? Oh, it's just 1 0. Okay. That's the molarity of the base in the original problem. .053 liters. Now, why do you think I'm saying I want it in mils? Give me a guess. We're doing a titration. It's not that we don't deal with liters. Think specifically about Yes, the burette is in milliliters, okay? So our burettes, that's their calibration, so that's what we're going to use. Now, here's the deal. Because looking at this equation, because we're at the equivalence point, in a strong, why do I keep doing the double freaking zeros? It's because I've been doing this many numbers for 2 hours now. 0.032, 0.032. So if you notice, we run out of acid and base and only make that much water, right? So you can see now why the pH is 7, okay? So in all strong, all of them, titration, strong acid, strong base, or strong base, strong acid in the beaker, all of them, your pH is going to be 7. And it's not going to be that way when we get to the weak strong. Okay, now we're at this point in the curve. I need to finish my curve out. I can't just stop my titration here. I need to finish to get that nice shape. I'm going to calculate the pH after adding 5 mils past the equivalence point. So this is still 0.0032, but here we have the 0.6 molar sodium hydroxide. Our equivalence point was at, what, 53.3. We're going to go 5 mils past that, so that's 58.3 times the 0.0583 times 0.6 gives us this is times 0.05. I'm just writing it down for people who don't know what's going on. 58.583. All right. So we're going to lose. We run out of that, and we are left with 0.03. Am I finally right? All right. 0.003. That's the number of moles of base. So my moles of OH is equal to 0.003. We're going to divide that by the total volume of 98.3 liters, 0.0983 liters. When I solve for this, what am I finding the concentration of? OH minus, be careful. So when you negative log it, it's actually POH. What do we get here? Is that right? And then, so my POH is equal to, is this number correct? So then you subtract, you end up getting a pH of 12.48. Okay, so when we sketch the curve, I literally want you to be able to do this and label your axes appropriately. So what I'm going to do is, I know I'm going up to, in this particular titration, to about 13. So I'm going to scale my y-axis to 13. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. And then I'm going to do my mils, I guess, in increments of 5, whatever. 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. I don't think I really ever get past that, do I? 65, 70 for just the mils of NaOH. All right. So before we even added any base, our pH was super low. It was like 0.0 something. So I'm just going to put that right there. So then I added 20 mils. What was my pH? Like 5, 10, 15, 20. Point 0.4. So we're about at a half of a pH unit at 20 mils. Okay. And then I added 5 after that. You guys have to help me look, especially those of you with paper. It takes you a second to turn back. What? How many mils? So this is 20, 25, 30, 35, 40 goes to a pH of 1, okay? And then 40, 45, 53. That's our equivalence point, right? 5, 1. Well, I can't. I'm not that close. 1, 2, 3, 4, 5, 6, 7. I can't get to 0.3 on my scaling. All right. And then 5 mils past that, what was our pH? This one? Yeah. Around 13. All right. So first thing I want you to notice about this guy, it has a very extreme start. Super duper low. It's pretty damn flat, and then bam, super sharp rise. And it continues, and it's going to level off. I technically should have probably done a couple more points within here, but I'm concerned that you understand the start of the curve. If we would have had a strong base in the beaker and then did the whole acid thing, our start would have been extremely high, 14 plus, really high up top. And again, we would have had nothing, 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 super sharp rise, and then the equivalence point is at what? pH equals 7. That is crucial in our strong, strong situation. Flat, sharp rise, nice, even, off curve. Got it? All right. So now let's take a look at, now this one's the beast because we're invading and we're making conjugates and we have buffer and hydrolysis and everything going on at one time. Because in this time, we're doing a strong base, weak acid titration. What's in the burette in this one? NaOH is in the burette, and we're adding it to a set number of moles of HOCl, or HClO, some of you know it. The Ka I wrote to the side on the board is 3.5 times 10 to the negative 8. You're going to need to use this number over and over and over again. Okay? So we want to know the pH before any addition of the base. So how do I find the pH of this acid? What kind of pH problem is this? A weak acid. How do I find the pH of a weak acid? Add it to water and put it in a rice table. So already it's become more difficult than the last one. So we don't care how many mils we have of it for this because we're just taking its concentration and finding pH. So we get x squared over 0.350 equals our Ka of 3.5 times 10 to the negative 8. X is equal to all right, and then that's going to be our concentration of H plus. So if we just take the negative log of that, you should get somewhere near 4. Go ahead and check it and make sure our K is right. 3 point what? Okay, close enough. So this is good enough. All right, so now we're going to actually start the titration. We're invading with sodium hydroxide into our HOCl. Oh, so invasion is a single-headed arrow. And we do this and we get OCl minus and water, and we don't care about the water. So to start with our stoic table, we need to know how many moles of each in the invasion. So we have 5 mils of the base, which is 0.2 molar, so that's 0.005 times 0.2, which is what? 0.001. And our HOCl, which is going to stay the same, is 0.024 times 0.350. 0.0084 and 0. So what's going to run out? The OH minus. This time we do have something we care about being created. So we have 0.0070 and 0.001. What do I have left over? The war is done. Oh, 7.4, my bad. 7.4. Now the war is done. What do we have left over? A buffer system. Do I use the pH or POH version? pH is equal to the negative log of your Ka, which is 3.5, times 10 to the negative 8, plus the log. What goes on top? Are you okay with me using moles? Why? It's a ratio. All right, pH is equal to, so 6.59 is correct. So already, look at the difference. Before we added 20 mils and we got to what, a pH of 1? We're up to adding, we only added 5 mils and we're already at a pH of 6.59. What do you predict the range of the equivalence point if we have a strong base weak acid? Strong base weak acid. Greater than 7. If we had a weak base strong acid, our equivalence point would be below 7. Okay, so that's something you have to pay attention to. But notice that already from the beginning it's different because we have a rise now. We've got a little hump. And that's not what we had in the last one. Okay, calculate the pH after the addition of 15 mils of base. So we're going to invade the Huckel and get Huckel minus and water. And this is still 0.0084. So now it's 0.2 times 0.015, which is 0.003. Make sure my math is right. 0.003 is going to be lost moles. And we're going to gain 0.003. So we're out of that. And then here we have 0.0054 and 0.003. What do we have left over? Again, another buffer. Another buffer. pH is equal to the negative log of 3.5 times 10 to the negative 8 plus the log, what goes on top? 0.003 over 0.0054. You should get a pH 7.2. Whoa. And we're past 7, and we are nowhere near the equivalence point yet. All right. Ready to move on again. Now we're going to add 25 mils of base. So again, we still have the set number of acid moles. And this time it's 0.025 times 0.2. So this is 0.005, right? Minus 0.005 minus 0.005 plus 0.005. 0.00. Woo. I can't line up numbers. I'm like a second grader. I have to have them lined up. 0.005. Okay. Notice how our conjugate base is kind of taking over the amounts. So here we had more acid than conjugate base. Here we have more base than conjugate acid. So we're converting more and more into that conjugate. So again, this is a buffer. pH is equal to the negative log of 3.5 E negative 8 plus the log of the concentration. We can use moles since it's a ratio. And you should get something in the neighborhood of 7.62. Okay, we're getting there. Calculate the pH after the addition of 35 mils of base. Oh my God. This will make you never take for granted a pH meter again. So, no, we're not going to. And the other one we could, because when we had the moles of the same equal, we were just making water. Here, you'll see a difference. Just hang on. We're not quite there yet. So OH minus is, this is 0.0084. And then this one is 0.035 times 0.2 is 0.007. I'm only multiplying that by 2 and hoping I have the right number of zeros at this point. Oh, Lord, 0.0014, 0.007. Again, we have a buffer. Notice all this buffering going on? What we're in right now is called the buffering region. From a little bit past the start through to the equivalence point, till right before the equivalence points hit, you have a region that's flat later on. Unlike the beginning, you have flat and then the sharp rise. So we are in the buffering region at this point. Negative log of 3.5 times 10 to the negative 8 plus the log of 0.007 over 0.0014. Good, 8.15. Okay, now we're going to calculate what we need to be at the equivalence point. Remember, at the equivalence point, here's the difference, why this is kind of cool, why we're not going to have a pH of 7. And it has to do with, well, we know this is 0.0084. So to be at the equivalence point, that has to be 0.0084 as well. The molarity of our acid was, our base was 0.2, right? We know we need to be at the equivalence point, 0.0084. And so how many mils? When you divide that by, when you divide 0.0084 by 0.2, we get 0.042 liters. But we actually are going to convert that to mils, so that's 42 mils. All right, big deal. What does that have to do with the pH? Well, let's go ahead and calculate that pH at the equivalence point. And this is why, Elsa, you can't get to 0, because here we have 0.0084. Because we're at the equivalence point, that's the same. We're going to lose 0.0084, but this time gain something that does contribute to pH, which is that conjugate base. So we have 0.0084. What am I left with now? What kind of problem do I have? It's not a buffer anymore. A salt. So we have now a hydrolysis problem. When we do a hydrolysis problem, I'm going to use half of this because I don't have enough room. We take our salt and add it to water, and we're in a rice table. So we get Hochul plus OH minus. The problem is, can I put 0.084 in there? 0.084? No, why not? It's got to be in concentration. So we got to figure out how much freaking volume we had. We haven't divided in a long time because it's been a buffer. We had originally 24 mils of acid, and we had how many mils? We just figured it out. 42 mils. So 24 plus 42. 66. So divide by 0.066 liters. So what is our concentration then? 0.3300. Now we're done with all that other information. We're going to start with our 0.33 and solve our rice table. We can drop our x, but we have a problem. 0.13 for this guy? Well, I might have just misheard. 0.13, 0.13. All right, so we get x squared over 0.13, but be careful, what is that? A base. Remember, anytime we have a hydrolysis problem, we have to convert Ka to Kb or vice versa. So we're going to have to take our Ka and divide it into that Kw. So our X, which is equal to our OH minus concentration, is 1.9 times 10 to the negative 11 is what I've heard. Yeah? Negative 4 or 1.4? 4.9 times 10 to the negative 11. All right, so if I take the negative log of that answer, I get a pOH of, no, You guys need to be careful with that. You need to pay attention to what you're taking the negative log of. You take the negative log of that, you get POH. What is that number? What? How did you get that? From here, you get OH. What is the OH minus concentration? 1.9 times 10 to the negative 4. Take the negative log of that. What, 0.72? And then 14 minus that? 10.31. 10.31 looks close. It should be 2, but yeah. All right. So that's at the equivalence point, and it makes sense because we have a strong base, weak acid. So our base being stronger is going to push that equivalence point above 7. Okay, the last part I'm writing here because it doesn't take a lot of space because now we're going to add 5 mils past that equivalence point. OH minus plus HOCl, again we're invading, and we're getting OCl minus in water. Our original moles here stays the same, 0.0084. Okay, we had 42 mils, 42 plus 5, 47, so 0.047 times 0.2, 0.0094. All right, minus 0.0. Now we're finally out of acid. We're done with the acid. That's gone. I know I have 0.0084 of this, but what's important? What did I say on Friday? What about strong? Yeah, strong wins. Whenever you have something strong left over, that's all you use for the concentration of your O. And this is going to be OH. This is moles of OH minus. We have to divide by the total mils. Holy crap balls, I'm already lost. So we used 66 plus 5. Is that right? 71. So 0.071 liters. So what's our concentration of OH minus? 0.0141. Our POH is equal to, yeah, because we're taking, look what we're taking the negative log of. 1.85, so then the pH is equal to, yep, there it is. So it's fun, huh? Good times. Let's go ahead and graph this one. All right, so 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2, 4, 6, 8, 10, 12, 14. So this is pH. This is mils of OH minus. So before we added any, what was our pH? Was it almost 3? 2.6? I don't remember. That's why I'm asking you guys. I'm not asking you because I want you to look it up. If I knew it by heart, I would do it. 3.99, so almost 4. All right. So then we added 5 mils, and we went up to 6 point something. I don't remember what. 6.6. So about halfway. Wow, we had somewhat of a hump there. And then how much did we add? 10, 15. And what was our pH? Okay. And then 15, then what? 20, 25. 7.6, okay. 30, 35. 8.15, okay. 42 was our equivalence point. Was that our equivalence point? Yeah, and what was that number? 10.3, okay. And then, so just 5 more than that, we were at, all right, thank you. Okay, so there's our curve. Now, notice we didn't start out as low because our acid was weak. So our pH isn't as low. And we have this quick start, and then all of a sudden we're like flat, 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 barely, barely, barely raising after all these mils. What was this area I said? We did the same calc over and over again. Yeah, this is our buffer region. And then we're getting to the point we're about to overtake that acid. And notice, is our rise as sharp as before? No. So it's not as sharp of a rise. Our equivalence point is 10. Does not equal 7. Okay. And then again, our start is not as extreme. Not as an extreme start. Okay? Now, there's one other piece of information about this that's really, really, really important. That only exists for weak strong. This does not exist for strong strong. And that's something called the half equivalence point. The half equivalence point is when I would have added, remember this was 0.0084, right? I would have added enough base to neutralize half of this. So how many moles of this would I need to neutralize half of it? 0.0042. So if I would have done that, plus 0.0042, I have here 0.0042 and here 0.0042, right? You've seen that before. What is true at this point about exactly? At the half equivalence point, pH is equal to the pKa. If it were a base, the pKb would be equal to the pOH. Why is that important? Sometimes you're going to get a curve, and all they're going to say is, hey, this is a weak acid curve with a strong base. What's the Ka? And you're like, I don't know. Give me a freaking table. You can figure it out from the halfway point or half equivalence point, also known as halfway point. How do you do that? Well, it's simple. Our equivalence point, we decided, was at how many mils? 42.2? What was it? The bell's about to ring. I need y'all to help me. 42-ish, okay? So if this was at 42, what is halfway to 42? 21. So 5, 10, 15, 20, 20, 5, 10, 15, 21-ish. I'm going to take it here. The pH of that to me looks to be about 7.5, right? And this is going to be ghetto because I'm doing this with a marker on a board. My scaling is not going to be perfect. So my pH at the equivalence, at the halfway point, is equal to 7.5. So if I were to say, hey, that's the pH, what is that also? The pKa, right? What would the Ka be? Figure it out. Put it in your calculators. 10 to the negative 7.5, and what do we get? 3.16 e negative 8. Look at the actual K, guys. Look how close that is with my ghetto graph. Okay? So if I ask you to find the K, you need to use the halfway point or the equivalence point to do that. Strong graphs, you have a halfway point, halfway to the equivalence point, but it's pointless because what are we making on the other side of the equation? Yeah, we're just making water. We're not making conjugates that are going to cancel out. So it's a useless thing on a strong graph. We care about it on a weak graph in order to find the Ka of the acid. All right, let me just sum it all up again. If the bell rings, don't move. I don't need much time. Weak strong versus strong. Extreme start, meaning high or low, not extreme. What else? Differences. Well, this one has a halfway point or a half equivalence, sure. What else about the curve? Sharp rise, not as sharp. Okay. What else? One more huge thing. Equivalence point is equal to 7, not equal to 7. Not equal, equivalence. And it's going to depend on whether the base is strong or the acid is strong to be whether it's above or below 7. Let me just show you real quick the different kinds of curves now. You should be able to look at a curve and tell me what combination you're using. So there's 4 different options. If I were to have this, what's in the burette? Base, strong base. In the beaker, strong acid. What if I have this? What's in the burette? Beaker. Okay. What if I have this? That's a horrible curve, but you get it. What's in the burette? Oh, wait, here. I guess I should have given you the equivalence point. We'll say this is 5. Equivalence point of 5. Weak acid. Weak acid in the beaker, right? No. Weak acid in the burette. Strong base in the beaker. And then if I had, that's not supposed to be a sharp. This is like 10. What's in the beaker? Weak acid in the beaker. Strong base in the burette. Okay, so you should be able to tell any combination of anything. There's actually 2 more we could do. Yeah.
So the difference between strong base, strong acid, and the top one is it doesn't have a
Correct. That's what leads you to, first off, know it's not strong. So that's the first thing you need to look at, and you can figure it out from there. So as far as tonight goes, I need you guys to watch the video for this problem. You have to watch the video. This is new to the AP, and it's going to show up. And then this next problem. After today's lecture, these shouldn't be too bad. And if you didn't watch it last night, this weekend, the previous video, you're going to have 30 minutes to watch instead of just 15. I want you to watch all of it by tomorrow.